So guys, in terms of, at the end of the last video was instantaneous rate, and to measure the instantaneous rate we need to get the slope of the curve that's produced as you measure the amount of product formed over a certain amount of time. So again, time is on the x-axis here, and you may assume that if you want to find the instantaneous rate at this, whatever this time is, let's say that goes up in 5, 10, 15, 20, 25, 30, at 30 seconds, you draw a straight line up and then create a tangent to the curve. And essentially what that means is to draw a straight line that touches the curve once and only once at that point there. And once you draw that line, you can draw it any length. We pick 2 points on it. So you could pick here and down here and get an x value and a y value here, just like in coordinate geometry. X value from the x-axis, so that'll be some time. A y value on this axis, which will be some value in terms of the amount of product, and likewise here an x value and a y value. It can be anywhere on the line, as that will give you the slope of the line, and the slope of the line off that line using y2 minus y1 over x2 minus x1 will give rise to the instantaneous rate at that particular point. So there's a big difference between the average rate, which is the rate over the entire, from the start of the reaction to the end of the reaction. And remember that the end of the reaction is when no more product has been formed or no more reactant has been consumed. So it ends here, it doesn't end over here because of that straight line there. And that average rate, if you like, will give it to over. It's like the average speed from here to Athlone, or from Dublin to Athlone. If you were to calculate the average speed, 100 kilometers an hour is not the average speed, it's the speed that's effectively over the entire length. Whereas if the guards were to check your speed at a particular point, they would use what's known as the instantaneous rate. That's what they're interested in, not your average speed, but your speed at a particular point. So they're two different things, and just be careful with the difference in two of them. I know we spoke about those before, just to be clear on it. The collision theory then, for reaction to occur, we've said this a few times now as well, for the reactions to occur, particles must collide, and particles must collide with the minimum amount of energy called the activation energy. So again, if you want to make an omelette and eggs are rolling around in a bowl, they have to collide with each other with sufficient energy such that the eggs crack. That sufficient energy to cause the eggs to crack would be equivalent to the activation energy. And in terms of chemicals, what you need is sufficient energy for bonds to be broken in the reactants, that then the rearrangement of particles or the rearrangement of atoms or polyatomic ions will result in a new product being formed, a new arrangement of atoms, if you like. We look at the collision theory and the activation energy in more detail at the end of the topic. Really in this part of the video what I want to look at is factors affecting the rate of reactions. The nature of reactants, particle size, concentration, temperature, catalysts, and then we look at catalysts in a separate one. So the nature of reactants is a most interesting one. When we talk about ionic or covalent compounds, you need to think about them and themselves. An ionic compound, when it's in solution, is effectively made, the solution has the ions, and let's say if it's dissolved in water, you have water. So there is no bonds to be broken as such. They're individual ions, for example Na plus and Cl minus floating around, and we'll look at an example of this in a second. And covalent compounds, when they're dissolved in solution, they could be individual molecules. Therefore, they haven't split up. There is still covalent bonds. So by its very premise, if you think about it, ionic compounds, you're going to have individual ions in solution, and covalent compounds, you're going to require some bonds to be broken and bonds to be made. So that's why it is much faster for an ionic substance to react rather than covalent. To give an example, sodium chloride, this is one of the experiments on leaving cert chemistry as well, to show the presence of chloride ions. We use, this is in test for anions, if you like, anions being the negatively charged atoms or negatively charged ions or polyatomic ions. So this is a polyatomic ion because there's more than one atom in the ion, if you like. But what we use is Ag plus, which is a monoatomic ion, and there you have Cl minus, which is a monoatomic ion. When you put silver ion in the presence of chlorine ion, they come together to form a white solid silver chloride. And that's one of the experiments you do. The reason that reaction is so fast, and it shows then that the chloride ions are present, that white precipitate, then this gives rise to the fact that all you have is the coming together of ions. There is no real bonds to be broken in either of these, because when they're in solution, they're individual ions. So it's just coming together of ions, no bonds to be broken, no bonds to be broken in the reactants, if you like. So you mix the solution sodium chloride and silver nitrate, and you get a white precipitate of silver chloride, and it forms effectively instantaneously. And you remember that as well. So the ions are free to move in solution, and there's no bonds to be broken. And that's the, you can evaporate it off, and you'll be left with the silver nitrate at the end. The pale yellow, this is a nice example. This experiment comes in a couple of times in your course, and you looked at these experiments as well and as part of this chapter. But hydrochloric acid and sodium thiosulfate, these reactions are much slower than ionic reactions. That is quite simply because bonds have to be broken and bonds have to be made. Remember, the reactants, if you like, when you look at this side of the reaction, the reactants are on their own initially, and when you mix them together, then in this case some bonds have to be broken and some bonds have to be made. So this is a relatively slow reaction, and it's a slow reaction in that there's bonds have to be broken in this thiosulfate part. Now that's called sodium thiosulfate because thio is a prefix for sulfur, so it's like saying sodium, sulfur, sulfurate. And remember, ending in ate indicates that oxygen is also present, as well as the two named elements, so sodium thiosulfate. We look at this a few different times, but you should know the name for that chemical and the chemical formula for it. But again, just remember that it's like saying sodium or sodium sulfur sulfurate, otherwise known as sodium thiosulfate. The thio just adding another sulfur there. As opposed to the sulfate ion, which is just, or sulfite ion, which is just SO3. What is formed here is sodium, sulfur dioxide, water, and then the presence of this sulfur is a yellow precipitate. So as the reaction goes forward, you'll get this yellow precipitate, and that yellow precipitate forms a cloudy appearance. And that effectively, the nature reactants is to bring it together. The reason that covalent reactions are slower is because bonds have to be broken, bonds have to be made. In ionic solutions, really all you have is the coming together of ions. Particle size is the other one. Why some reactions are faster than others. Like if you were to take a cube of sugar and put it into a cup of hot water, or you were to take granulated sugar, which one of those would melt faster in the water? And you have to think about that, and if you think about it, or you experienced it, and even chunks of sugar, this one, the larger particle, will take a lot longer to melt. And that is because chemicals, and indeed energy, is quite superficial. It only acts on the outside, in terms of heat energy at least. It only acts on the outside, and chemicals definitely that way. They only act on the outside because essentially the molecules on the inside aren't exposed to whatever is outside. Therefore, they're not going to react with it. And then gradually it makes its way in and makes its way in. It's similar to iron rusting, like iron rusts with a combination of oxygen and water in the air. It's only the surface that's affected first, and then gradually the iron flakes off to expose more iron, and you effectively get it to turn it into iron oxide. And there's the smaller particles. All the surface in here is exposed. Even though it's the same mass of sugar, let's say, all these surfaces are exposed to the water. And it's the same for chemicals. If you have more surface exposed, then chemicals can react. And we'll look at a nice application of that in a catalytic converter and a different one. Another application of it is actually dust explosions. This is a picture of a dust explosion. What happens here is the particles are so small that the air can hold them somewhat, similar to that of Brownian motion in liquid water. So the particles are somewhat suspended in the air, and it happens in flour mills or cement factories. And the particles suspended in the air, they almost act like a gas. So all you really need is an ignition source. And the ignition source sometimes can be someone touching something metal after building up static electricity. So that's why it's really important in these factories that any metal equipment is earthed. So it's connected to the earth so that there's no, or at least there's a reduced chance of creating a spark. You need three conditions really. You need a suspended combustible material like flour essentially. It needs to be suspended in the air somewhat, easily suspended. And the third thing is you need a supply of oxygen. So those things are all necessary there. The combustible, and then the ignition source is normally some sort of spark, for example. To investigate the particle size and the rate of reaction, this is an experiment you look at junior cert as well. There's hydrochloric acid, calcium carbonate at junior cert you would have called marble chips. You mix the two of those together, you get calcium chloride, water and carbon dioxide. So the reason you do it for junior cycle, if you like, or junior cert, is to create carbon dioxide. But if we were to look at it, this is an interesting one because when we're measuring the rate of this reaction, what we're actually going to do is not measure the amount of product formed, but the amount of reactant consumed. And the easiest way to do that is simply by measuring the mass. Initially, you would have the hydrochloric acid on its own, you'd have the marble chips on their own, and then you pour in the marble chips or calcium carbonate, and the hydrochloric acid will react with the marble chips, giving off carbon dioxide. The carbon dioxide will try to escape. You have a loss of mass in terms of downward force here, but obviously you know that you cannot destroy that mass. It's just that the carbon dioxide is leaving through a gas going through this cotton wool, if you like. The purpose of that as well is to stop acid spray from being released to the surroundings. So because you only want the loss of the calcium carbonate, if you like. And the reason it's reducing in mass, remember, is that the carbon dioxide is going out here. It is not being destroyed. But in any case, the way that you would do it then is to try and you do two different experiments. One with marble chips or calcium carbonate broken up quite a lot. Make sure, obviously, that it's a fair test, that you would have the same mass of calcium carbonate here as you would have here. Break it up as much as possible. And then on this side, you'd have larger chips. You have a lot of surface area exposed here, not so much surface area exposed here. You allow the mass to decrease, as it will decrease, and indicate then the drop. And you'll find that the rate of decrease of mass of this one will be quicker than the rate of the decrease of mass of this one. And that's simply because there's more surface of the calcium carbonate exposed to the hydrochloric acid, and that's why it decreases quicker. Similarly to what we said earlier in terms of sugar melting, a cube of sugar or granulated sugar. The concentration of reactants, a nice way to explain this is that, if you like, at the start of any reaction you have the maximum amount of each reactant. Considering you're putting two things into a conical flask, let's say. And you have to think about that that the maximum amount of both reactants, or whatever number of reactants are there, therefore there's going to be a maximum amount of collisions. And if there's a maximum amount of collisions, as the reaction goes on, obviously the amount, considering you don't put in more reactants, the amount of reactants is going to decrease over time. And that is essentially why you have less collisions, the reaction starts to slow down. Just quite simply because there's less of them present. So here you see there's a higher concentration, a slightly lower concentration, and the lowest concentration, and over time they will decrease. Hydrochloric acid, sodium thiosulfate, and there's the sodium chloride formed again, and sulfur. So we looked at this reaction earlier, and what we were going to do in this case, we're going to look at the production of sulfur. Now the great thing about sulfur is a pale yellow precipitate in water, so when you look at it, it will actually cause a cloudiness to appear. So the principle of the experiment is very straightforward. You add the HCl to the sodium thiosulfate in the flask, you look straight down. So you're looking as a plan view, if you like, to look straight down and look at, mark an X on a page and start the clock when you've added the HCl, and then measure the length of time it takes for this X below to become obscured or disappear effectively. And then what you would do is you would throw that one out, rinse it out, and use different concentrations. So for example, you could use concentration 0.2, 0.16, 0.12, 0.08, 0.04 and 0.02 and measure the length of time for the X to obscure. And you'll find that for the more concentrated ones, the X will obscure much faster than the less concentrated ones. And that's the effect of concentration effectively. And the rate is proportional to directly proportional to the concentration, because of the more collisions, the reaction will happen faster. The temperature, the rate increases rapidly with the temperature for two reasons. The reactant molecules will have greater energy, therefore more of them will have sufficient energy to get over the activation energy, and the collisions between the molecules will occur more frequently. And that's a relatively simple idea as well to carry out an experiment. It's the same chemicals we use. This time we don't change the concentration of HCl, we just change the temperature of the solution. And we do that by heating it, very simply. We do it at hopefully you do it at about 5 different temperatures, and you'll see that the X will obscure much quicker at the higher temperatures. Therefore, the reaction is affected by the temperature. And now this curve as well, there's a lot to be said for this curve in terms of, there's a lot of chemistry here, the idea is there would be a point where you'd no matter how much you heat it, you're talking about it going into evaporating or maximum amount of collisions occurring at that temperature. So it does flatten out, if you like. The main factor is increase between A and B is due to the increase in collisions per second. And that brings us then to the end of the collision theory, and we start going in then to the catalyst. So that's in another one.